You up. So this next section, next half of the day, is all focused on different sectors within Nebraska and how climate relates to each of those sectors. We probably can't do enough justice to, bring every sector to and everything that's going on in each of those. So we'll try to do a little bit of a highlight. This first one is going to be on agriculture. So we're going to do it in an hour, right? We're going to tell you everything there is to know about climate and agriculture in an hour. It's actually probably a 3-week all-day conference to cover a number of the topics here. So we kind of just wanted to do a little bit of snippet of what's happening in the state. And then hopefully, if nothing else, you can put a face to and a name together on a topic that interests you. So first up, we're going to bring up Dr. Galen Erickson. He's a professor of animal science at UNL. He's done a lot of work with ruminant nutrition and feedlot management. I think he's a feedlot specialist. And he does a lot of work with methane. And in this climate world, methane gets a lot of publicity. So we thought, great to have him come up and talk to us. So I'm going to go ahead and turn it over to you and let you go from there. Here's a lapel if you prefer.
And the pointers.
Yep. This thing works.
Very good. Can you hear me okay? Yeah? Well, it's good to be here and talk with you about this. I certainly want to recognize that there are students, Tommy Winders and Levi McPhillips and other faculty that are involved in this process, right? So from this morning, I'm going to talk a little bit more about specifics and related to beef cattle. This is my favorite picture. I think all steaks sold in Nebraska should look like that. But obviously the quality grade for beef cattle is the best quality is prime. So notice it's got a prime flag there. We are in a fairly prime spot to produce beef. So I'm going to talk a little bit about how methane's produced by cattle. It's a natural process, and we're trying to manipulate that natural process. But probably my biggest concern is that some people suggest, well, one way to fix this is to just not have beef cattle. Hopefully by the end of this, you'll understand that there's some value to why we have it. The other thing I want to show you, which is probably different than what's been discussed, is how this is measured. And I recognize none of you are going to run out and start to measure this like we are, but I also want to impress upon you that it's not easy to measure, but a lot of people put out numbers of how much methane's produced. Not many people are measuring it, and I want you to have some small appreciation for that. Okay, so a colleague of mine who's a rumen microbiologist is very interested in this too, Samota Fernando. So that's his picture. Methane is a microbial process. So that's why methane's produced in wetlands. The wetlands producing methane because there's microbes that are generating it. And there's a specific kinds of microbes called archaea that produce methane. And there's a reason why it's produced in the rumen, okay? So if you don't know what cattle are or what a ruminant is, well, I think everybody should, because obviously that's what I do, right? But they're different than you and I. Cattle can graze. Sheep can graze. Now horses can graze too, but they're not a ruminant. Now what makes a ruminant is they've got this big fermentation vat. That's the first thing that the feed goes into. And it's full of microbes. And when cattle are out grazing grass, cattle cannot digest the fiber that's in grass. They don't have the enzymes. Cattle are just like you and I in that regard. But they can go out and graze all this fiber. It goes into this rumen, and then the microbes are the ones that produce the enzymes that actually digest fiber or cellulose compared to non-ruminants. In that process, the microbes grow themselves, so they make protein for the animal, and they convert the fiber into energy that the cattle can use. So you've got a cow that's out grazing grass, she would die without those microbes. Okay, so it's not something we can just wipe out and say let's not use. And if you want to utilize all of the grasslands that are naturally around, then we need to have ruminants if we want to get protein off of those grasslands. So that's the big debate in my opinion. So how much is produced in terms of the methane and why that's produced, I'm going to briefly show you. But it's complex and it gets influenced by the type of diet we're feeding. But every place that you read about methane production, the anthropogenic or the human methane production, we say cattle that produce methane is because humans are raising those cattle for food. When we do these studies, people like, well, I don't say we, Samoda and his students, we collect samples out of that rumen, right, where those microbes been growing, and he analyzes them, and what we feed influences. So all I want you to understand from this graph is that all these cattle were fed a common diet, and that's what it looked like. Then we fed a low-quality forage diet or a high-quality forage diet, and then we sampled what the archaea distribution looked like inside those different diets. So just by looking across there, you can see that there are differences in certain types of archaea that are in those rumens and produce methane. So how we feed cattle does influence the type of bacteria and the type of methane generating bacteria that are in the rumen. And this is the type of graphs and distribution. So one way to influence this is to feed different diets. So I'm going to show you that feeding just different diets influences how much methane is produced. That's what I'm interested in. I'm interested in what can we do differently to feed them or add to their diet that will decrease methane that's naturally being produced inside their rumen. Okay, but you know what? We can't just get rid of it. Unfortunately, I don't think that there's a way biologically to just wipe it out. And the reason why is because the methane generating bacteria serve a very key role in this ecosystem of the rumen. Okay, so some people would say, well, let's just wipe them out. Well, if we do that, the cattle aren't going to do well, and it redistributes the whole ecosystem. And the reason why is because the methane generating bacteria, methanogens, are combining CO2 and hydrogen to reduce that environment and accept hydrogens. There are other ways to do that, okay? But one is through sulfate reducers. Well, that's also a toxic mechanism inside cattle. If you overfeed sulfur to cattle, it can kill them. Nitrate's another thing that you could use. Nitrate's another way if you want to end the animal's life early. You feed them a lot of nitrate. You see my point? So there's other ways to do it, but they're not very suitable, at least in my opinion, ways. Okay, so that's so I guess my point of those first slides is this happens somewhat naturally inside the rumen. There's a reason why there's methane being generated, and it's influenced by what we feed, and maybe we can influence it some, but we can't just wipe it out. Cattle or livestock, or obviously you've seen some of this, contribute to this concern. It's debatable what those percentages are, and it's debatable because, frankly, it's based on numbers that people have estimated. So that's why later on when I talk about how it's measured, we're trying to get to some better numbers, I think, than what's out there. But either way, you know, it's probably about 4% contributed from agriculture, from livestock, and beef cattle are a big component of that, mainly because they produce methane during their production and lifespan. Okay, so we have a research facility that's 45 minutes north of us near Mead, Nebraska, called the Eastern Nebraska Research and Extension Center. And we first started doing this work, I say the early years, this was about 8 years ago, that's not that early. We thought when cattle come in to a feed bunk, these are their feed bunks, they individually come in, they stick their head in there, they're breathing while they're eating. And when they're breathing, they can expel methane and CO2, and we could just capture some of that and use CO2 as a marker. So we were pumping air out of this enclosure when the cattle stuck their head in there. And then we would sample those cattle, so you can see that we're tubing that animal and literally pulling contents out of their rumen to sample and analyze for bacteria and archaea. And you might think, well, that's kind of gross. That can't be good for the cattle. Does everybody understand what ruminating means? What cattle do when they ruminate? They literally spit their food. This isn't pleasant to talk about after lunch, is it? They literally regurgitate, which is a nice way of saying they spit their food back up. They re-chew it, and then they re-swallow it. My kids think that's pretty awesome, but that's what they do. And they do that because they go out and they graze a bunch of grass as fast as they can, go lay down somewhere and chew their cud. When they're chewing their cud, that's what they're doing, right? They're spitting it back up, re-chewing it. So my point is, us pulling some feed out of their rumen's not that gross to them because they do it themselves all the time. Then we wanted to compare that system to a much more controlled environment. We call them head boxes. Everybody talks about, I apologize for my language, I have a lot of bosses here, cow farts. You've heard that term? It's terrible. You know why? Because that's not how it works. About 10% goes out that end, 90% of it's going out the front. Okay, so this isn't a flatulence problem. So we measure them, what's coming out of the front end by literally enclosing their head in a head box for a day. They're eating out of there, they're drinking, so it's not harmful. And then we measure how much oxygen and CO2 and methane is going into the box. We measure how much oxygen, CO2, and methane is going out of the box. We know how much air flowed through the box, and we can calculate how much methane they generate. Does that make sense? So it's a very accurate way. The cattle, I said they don't mind it. They don't like being, confined to this box for a day. So they eat a little less that day. So it's not perfect. And those boxes are expensive. So you can only measure a handful of animals at a time. So there's limitations to it. But we compared the head box to what we were doing in that other method. And we did it on high quality and low quality diets. And while there's some agreement there, we thought it's not robust enough. So we went to other methods. So we built more boxes. This is actually our dairy nutritionist. Dairy cattle have the same challenge that beef cattle do. Our dairy nutrition folks are very interested in cutting methane. He's built a lot of boxes. And so we got more boxes, and these are just, you can see pictures of us measuring those cattle. They can sit up and down and so on in those boxes. So I'm going to show you probably a little more data than what you've seen so far, but I'll try to just hit the high points and then make some conclusions. I want to start off with some work we did on biochar. Biochar is getting a lot of press, and this just got accepted in the scientific literature, what I'm going to present to you. Fortunate to work with High Plains. Biochar was the type that we were using. You can see what it looks like, and this work was funded by the Nebraska Forest Service. So we fed 0, 0.8, and 3% of the diet is biochar. Now, I've got to tell you, it is illegal to feed biochar to cattle and then take those cattle to market and consume that meat. You know why it's illegal? Because this biochar has not been approved to be fed to cattle, and then those cattle enter the food supply. So if we're going to do this, which we did, right? I just told you we fed it. We can't slaughter those cattle and make them into those Nebraska steaks. Does that make sense? So you don't want to use very many, because when they get done, they are euthanized and have to be incinerated or rendered. Or not even rendered, I'm sorry. Composted or buried or incinerated. So they didn't enter the food supply. That's why we didn't use very many, and that's why we used the head box. So feeding 0 versus 0.8 versus 3, the middle line right here, 109 grams of methane produced per day on the control, 97 to 101 if we fed the 2 levels of biochar, which frankly doesn't seem like much, right? But I'm pretty excited about that it had that much of an impact. But remember I said we can't get it to 0 very easily. So just decreasing it, what is that, 15% is a fairly, 11%, a fairly big improvement. So all these other things are just other things we measured, like digestible energy intake, carbon dioxide, we also measured, and they expelled or exhaled less CO2 in that process too. That was in forage-based diets. Then we also did this in finishing kind of diets. Okay, so I need to stop for a second. There's 2 major kinds of diets we can feed to cattle. In general, they're classified into 2 categories. Forage or fiber-based diets, cows, cattle that are out grazing grass or growing calves are all fed those kind of forage-based diets. And then there's finishing diets. That's my area of, if I have an area of expertise, I'm in the finishing side. Feeding them more grain, byproducts, more energy, putting on more weight faster and more fat. So the first study was with forage-based diets. This is a finishing-based diet with 50% corn, 15% silage, 25% byproduct. Again, either 0, 0.3, or 0.8 or 3% biochar. In this study, 140 grams per day in the control, 127 or 122 with the 2 levels of biochar. I do have to point out, I've given you all the statistics. Half of you won't care about that. In this study, there was not enough power. We didn't replicate it with enough cattle for that to be a significant decrease. I think it's biologically important, and as soon as we get the approval and more funding, we'll feed biochar to more cattle to make sure that number is biologically and statistically decreased. Okay, the other mechanism that we've used is a bigger chamber. Because remember, if we're doing this 1 animal at a time, you can do 6 animals at a time. Maybe across 6 months you'll get 30 observations. That's not very many. So we thought we need a big chamber. There's 2 other places I know of in the US that can do this type of work. One's in Michigan, one's in California. And so we wanted to build a barn where we bring a pen of cattle in, and just like a head box, measure CO2 and methane going into the barn, CO2 and methane going out of the barn, how much airflow. You can calculate how much methane they're generating. So we modified a couple of barns that we have at our research facility. Above these garage doors, there's air inlets. A garage door literally every day they come along with the feed truck, open the garage door, feed the cattle, close the garage door really fast, try and minimize how much air is let in. Air is mixing in this facility. There's a sensor right here that goes to our methane and CO2 analyzers that's pumped from each of these barns, and it's a negative pressure. Dr. Rick Stoll, one of our biological systems engineers, helped us construct this whole system. Using the LICOR methane and CO2 analyzers, it is very robust. So those cattle are in those barns. We have 2 of them, so we can test 2 different treatments, rotate cattle through from pens throughout time, and every 20-minute cycle, we measure those 2 barns. So this is methane on the y-axis. There's a 2-minute clean-out cycle. Then there's 6 minutes in one barn. You can see that the methane concentration in the atmosphere is around 3 parts per million. That jumped in this first barn to over 25. Then for 6 minutes, measured that methane concentration. 6 minutes, measured ambient concentration south of the barn, so we knew how much methane is going in. Then it rotated to the second barn, and in this particular cycle, that was a little over 20 parts per million. So you see the point. We're measuring robustly every 20 minutes for a 5-day period. I can tell you pretty darn close how much methane is coming out of those cattle and CO2. So we tested this in a forage-based diet. We fed those diets ad libitum, hopefully the way you had lunch, which means as much as you want, right, at one's pleasure. Hopefully everybody ate exactly as much lunch as they wanted. You were ad libitum. Maybe I should have been on a restricted amount and restricted how much lunch I had. Does that make sense? So we had the same diet being fed to the cattle. We just let them eat as much as they wanted, or we gave them 75% as much as what they would want. Is that clear to everybody? And when we did that, guess what? 156 grams a day of methane versus 126, very significant. That's different whether it's not different if you express it as a unit of intake. It is different. It is not different either if you express it as a unit of gain. So my point is this. One way to cut methane is make cattle eat less. You know what's going to happen if they eat less? If they eat less, they also gain less. So they'll be around for more days and produce methane for longer, but they will produce less per day. Does that make sense? So this isn't a good strategy. But we wanted to illustrate that point. Another strategy we've tried, the Canadians have done a lot of work in this regard, is feeding oil, a fat. So in this case, we fed 3% corn oil to finishing cattle versus none. And we measure performance. Good thing about oil is they tend to gain as well or better, and they do it better in terms of efficiency, so it takes less pounds of feed to put on gain. But when we look at methane, it also decreases methane. So in this finishing study, they produced 132 grams a day compared to 115. So I guess the general comments I wanted to make, I've got another point I want to make at the end of this. So I have conclusions up there, but it's not my concluding slide, so I'm just forewarning you. Hopefully you're not tired yet. Methane coming from cattle is a natural process. So I don't want anybody to go away thinking that it's unnatural and that it's not something that we could just change or that we're inducing, okay? It's a microbial mediated process, and unless we make cattle into non-ruminants, which I don't think is a good idea, we're going to have to work on this. Diet impacts how much they produce. Generally speaking, if we feed fiber or forage diets, they do produce more methane, at least on a per unit of energy or productive function. So some people think, well, we should just put them all in a feedlot like what I do, okay? And that does decrease the amount of methane because it speeds up how fast those cattle grow, so they're theoretically around less time. Does that make sense? I'm going to come back to that issue. I certainly think that we need to find additives like a biochar. There are others that have been tested. I've just given you a sampling of some that will actually cut that without hurting anything related to how the cattle perform. That's what we need to, that's my goal, and I think that's something that would help. Now, the last comment I would make is that these things need to be measured. So why did I show you the head boxes? Why did I show you what our sort of first attempt was? Why did I show you the barn? Is because we need to be measuring these things. People can't just be putting out numbers. And then I'm interested in measuring those types of things in all the different ways that we raise beef cattle in the state of Nebraska and elsewhere. So then we can start figuring out what is that way of raising them or production, how does that influence how much methane we have? Not just in terms of how fast they gain or perform, but how much methane are they producing. That should be a goal. Because otherwise, everybody's just putting out numbers and they're not necessarily perfectly accurate. That's the only way I think we're going to improve. Now, the last comment I'd make, even as a feedlot person, yeah, we can feed them all grain. That doesn't capitalize on some of our natural resources, and there's other implications if we just put them all in a feedlot, such as water, such as ammonia, other things that we're measuring here at the University of Nebraska. So we've looked at, should we just put all these cows in feedlot pens? We've done intensive cow projects. Rick Rasby was involved in that. There's been 5 years of data collected on a project. It's been very successful, okay? Now we're doing some of that work, but now we're adding in methane production as part of that. Before I end, I want to emphasize, even as a feedlot person, how much forage we feed. The bottom line, this is taking an animal that gets to market. So if you have a steak tonight, okay, how much did it take to get that steak to market, that animal to market? Does that make sense? So on a per animal basis, that animal is raised by a mama cow, okay, so there's a cow somewhere that had that animal as a calf, and in the U.S., in general, that calf stays with that cow for 7 months. Now, this sounds a little bit rude, but that cow is around for one reason. That reason for that cow is to have that one calf every year for as many years as she's reproductively capable. I don't mean that in a crude way, but everybody understand the beef cow that's out there that you see, her job, so to speak, is to raise that calf for 7 months. And then hopefully raise another one next year at the same time. Is that clear to everybody? So we wouldn't have cows, beef cows, if we don't have calves. So my point is how much a cow eats is completely there because it's going to have that calf. So when that animal goes to market, all the cow needs have to be put on that calf. Does that make sense to everybody? So if you add in how much the cow eats, it's about 7,000 pounds of forage for that 7 months. But then she's not doing anything except for raising the next one inside of her, gestating for 5 months. So we got to count that feed. Then we're going to put that calf on forage for a while, so we got to count that feed. These are all pounds of forage. And then when we put them in the feedlot, we're going to still feed them a little bit of forage. If you add all that up, it's about 14,000 pounds of forage without any grain being fed to the cattle. Does that make sense to everybody? Now, unfortunately, not every cow gets every calf to market, or not every cow gets bred, that kind of thing. And then even when it does, we got to take some of those baby females and replace those cows eventually. So if you count for that, it comes out to be about 18,000 pounds of forage. Is that clear to everybody? We feed them about 3,300 pounds of corn. So everybody thinks in the U.S., especially people that do my job, we feed all that grain to cattle, right? It's a small proportion. Less than 15% would be non-forage. And by the way, that 3,300 pounds, at least in a state like Nebraska, would only be 50, 60% grain. We do not feed a lot of grain to our beef industry complex, okay? And yet, we're the most efficient beef production system in the world, much more than any other country, excluding maybe Canada, because they do it just like we do. Does that make sense to everybody? So with 15% of our feed needs going into our beef complexes being grain, we're still the most efficient. Now, when I say the most efficient, we have about 100 million head of cattle in the U.S., and we raise more beef than Brazil that has 200 million head of cows. Does that make sense to everybody? They have twice as many animals and produce about 80% of the amount of beef that we do. Why? Because we feed them grain at the end, we manage them intensely. So my point is that we're not going to take away 85% of the feed to solve this methane problem. Nor should we, because that's how we're utilizing our natural resources at the grasslands. With all that said, the red dots are places that lost cows from 2007 to 2012. The blue dots are places that increased cows across the U.S. Generally speaking, we're losing cows on grasslands across the middle part of the U.S. We want to figure out ways to solve that. One way to solve that is to take traditional farming areas like eastern Nebraska, when we don't have natural disasters, and put more cows on it. How much time do I have? So we're doing a project to try and raise more cows, and it's not mine, I'm just a part of it. But in that process of raising more cows on these farming areas, we're also monitoring how much greenhouse gas emissions are from that system versus a traditional system. Now it's really tough work. Andy Syker and others in the School of Natural Resources are using micrometeorological techniques. So 10 times a second, there's a measurement of methane on that tower, as well as wind speed and wind direction. That's a lot of measurements when you leave it out there for 365 days, right? So it's a very intense way of measuring how much emissions are coming from this pasture with grazing cattle, this other pasture, or grazing corn stalks, grazing cover crops, measuring it in pens. But when they're out there grazing, we got to know where those cattle are. So this steer has a GPS collar on him. So we're measuring those two systems. So now we've measured it in the head box, in a pen, and now we're trying to measure it in these big pastures and pens to make it apply to what we're doing in the state. With that, I'd end, and I think we're going to take questions later.
Yeah.
Okay.
Okay, thanks, Galen.
You want this or do you want that?
You like this one? Whatever one you want. So he's the first one that I've ever seen put a conclusion slide up, and you still had 6 more slides. I don't know if I've ever seen anyone do that tactic, but I think that works. I think that's a good idea. I might have to start using that. Oh, sorry, I didn't need to click the button. Okay, so next up, that was kind of our little hit on the livestock section, and the next half will be mostly on crops and soils. So we have, glad to have Dr. Andrea Basche. Did I say that right?
Yes.
Yes, I did it. She's an assistant professor in the Department of Agronomy and Horticulture, and she's done a lot of work with cover crops and soil health. And her research focuses primarily on the agronomic benefits and trade-offs of diversified cropping systems, including perennial crops and cover crops. That'll kind of be the thing that she talks about today, and she'll speak a little more on the opportunities that soil health might offer for managing water-related climate risks. So thank you, Andrea, and I'll kick it over to you.
Thank you. Thanks, Tyler. I appreciate the invitation. So I'm going to totally shift gears from what Galen just talked about. As Tyler said, and the speakers that will follow will be more on the crop and soil sides of things. So I want to talk in my brief time that I have today about soil and how it can help us manage water-related risks like floods and droughts. And as we heard about this morning, we know with some certainty that we have to manage increasing rainfall variability. So we know that with certainty. We're seeing this increase in heavy rain events. And we know that it's not just what's happened in the past, we know what's happening right now. So I feel like I'd be remiss if I didn't talk briefly about the flooding that's happening around us. So it's tragic, it's devastating. We don't yet know the full impacts of it yet, right? So this is a picture actually from my partner's family's farm, which is in St. Paul on the Middle Loop River, and the tree line is supposed to be where the Middle Loop is, but you can see that it's come onto their farmland. We're actually headed up there this evening, not just to see it, to visit, but get a look at it myself. But from what I understand, that they've lost a huge part of their farmland. So they have about 300 acres that's been in alfalfa for several years. So that area, in terms of the sand deposition and the major soil erosion that's happened, is going to take, I would imagine, years to decades to restore its productivity. And this flooding that's happened, right, speaks to this perfect storm of things that happened starting last fall with a very wet season, having bodies of water that are full, continuing with the cold and snow-filled winter that we had, and then, tapped by that heavy storm event that just dumped water on an essentially impenetrable land surface, right? So this is the kind of stuff that really keeps me up at night. I'm thinking about when I go to my students next week, how do we talk about what options we have for the future on this front? And so the reality in events like this is that we end up losing soil at a rate far greater than it's naturally replaced. So I actually looked into and was asking Tyler before, how do we place this event into context? And my quick scan of the NOAA billion-dollar disaster database is that, and if you heard the news this morning, that $1.4 billion is the early estimates of what damages will be, and I'm sure it will end up being more, but I couldn't find any winter flooding events in this part of the region that have been this damaging, at least from an economic standpoint. So I'm really thinking about the future and what do we do? Are there some important research questions we might ask about different flood reclamation aspects? Because how we deal with water is just going to be so critical for our future as we are living through right now. So on that note, I wanted to give you a few reminders about the soil and how a healthier soil relates to water. So I thought I might start with the water cycle. So essentially what the water cycle is, right, is just the continuous movement of water molecules through the atmosphere and the Earth's surface. And what are the important components for us in an agricultural context for the water cycle, right? It might seem pretty obvious, but we have precipitation, right? So the amount of rainfall we get, that's important, obviously, for agriculture. How we manage our surface water and our groundwater for irrigation, that's obviously important. The water that's lost from the land surface, evaporation, or the water that crops use, that's transpiration. And then finally, these are my favorite parts of the water cycle, which is, if one can have favorite parts, these are mine. So the water that gets into the soil surface, the water that runs over the soil surface, or the water that stays in the soil, right? So infiltration, runoff, and soil moisture. So those are really, major important components of the water cycle that we think about for agriculture. But what we're really trying to do when we're thinking about agriculture producers research, we're trying to manage the water balance. So all those aspects that I just talked about. So how do we maximize the use of precipitation so that crops can grow and do their thing, take up nutrients, produce yield that we want to harvest? And then how do we also prevent losses of water by things like evaporation and runoff? And when I think about this, this balance here, I have the soil in the middle. The soil is really a central reservoir for managing those in and out flows of the water cycle. And just to drive that home, this is really how I think about the soil surface and the soil profile. It's really, again, that central component that's regulating the in and out flows of the water cycle. So if I say that in a different way, right, the soil surface is really where the action's happening. So that's where water is getting into the soil, that's where it's being held, and where plants are taking it up. So hopefully I've convinced you or given you a little bit more interest here in why I think about what's happening at the soil surface and some of these processes, because I see that as so critical to how we manage water. So now that I've talked some about the importance of the soil surface, I also want to shift to talk about soil health. So what is soil health? So soil health is a topic that some soil scientists love to disagree about what it means, but I'm an agronomist and not a soil scientist. And so for me, it's very straightforward, right? Soil health is this concept that we can have the continued capacity of the soil to function and to sustain life, and that it can be sustained for future generations. We might also refer to soil health as soil quality, soil tilth. But these ideas, the functioning of the biology, the chemistry, and the physical components of the soil really, for me, fit nicely into how we think about water management. So how many people have seen these infographics before? Okay, I see a few hands, not too many. So these are popular infographics developed by the USDA that talk about healthier soils, the value that they can hold in terms of storing more water. And I want to just show you, I only have 2 research-related slides here about my own research that supports some of these ideas behind and the numbers behind these infographics. So I worked on a large review in a prior role. Some of this has been published in a few different papers about how well do various management practices impact infiltration rates. So again, that's the rate that water enters the soil, and because that's so fundamental to water staying in the soil, right? It's got to get there. That's step 1. So the practices that we considered in this big review, these came from published studies. What I'm showing here was about a year of my life, which is kind of sad or exciting to admit, I don't know. But we looked at a range of different practices compared to what we might associate with more conventional controls. So this represents over about 120 studies that have been published around the world. And so we looked at things like no-till compared to conventional tillage, crop rotations compared to monoculture, cover crops compared to no cover crops. So a range of different practices as you see here. And what we found, I don't have any numbers here, I just wanted to show you kind of the magnitude of change that we saw in all these studies in terms of the improvement that they offered in increasing infiltration rates. It's going from left to right here, that perennials offered the greatest benefit. And we did see some decline in infiltration when you had animals on grazing lands, on croplands, excuse me. But what's the common denominator here that we saw across this whole analysis is that the most effective way that we found to increase the rate at which water's entering the soil is continuous roots in the soil, right? So that was the most important thing for facilitating water entry and improving soil structure. And just one more kind of related piece of research from my dissertation data. I went to Iowa State for my PhD, and I collected data from a long-term research site that was a corn-soybean crop rotation with a cover crop grown continuously for about 10 years at the time we started this analysis, where we were looking at soil moisture sensors that were out there continuously, and I just have 3 graphs to show you from this, but we looked at a series of wetter and drier years in the record for how much water was stored. So this is a graph of soil water storage to 30 centimeters, and so this was 2012, and I'm sure many of you can remember that was the big drought year, really warm March. So in the beginning of that year, we did see, so the green line here is the cover crop treatment, and the no cover crop treatment was here in brown. And so the cover crop treatment started a little bit lower in terms of water storage earlier in the season, but by the end of the growing season was higher in the cover crop treatment, so this was a very dry year. And then moving on to 2013, which was a really wet spring and a wetter year overall, we had pretty consistently the cover crop storing more water in the soil there. And then a similar story in 2014. So 2014 was a bit more of an average year. So we did see this really nice evidence over a series of wetter and drier years that the continuous use of the cover crop was increasing water storage. And part of the reason that I am interested in some of these topics, and I joke that these are my favorite parts of the water cycle, when I talk to producers, they have so much experience with water retention, water infiltration. So I was a part of a focus group project. So we went around the state of Iowa, this was in 2014, and talked to producers who were using cover crops about some of their experience, some of their management successes and challenges. And so I don't need to read you the quote up on the slide, but you can see that this was a story that a producer was sharing about increased infiltration and heavy rain events. And I'm sure many of you have heard stories like this. It just seems like it's always something that comes up, a real source of pride for producers. And so that's all I have for you today. But I just, reiterating on a few main points here, right, that the soil surface, I'm thinking about this all the time, can really be a tool that we can manage. There are ways that we can do it through things like cover crops or having continuous roots in the soil that will improve the soil's capacity to infiltrate and store water. Yeah, and I would just encourage us all to think about this as an approach for the water risks that we'll have in the future and that we're experiencing now, that soil can be a solution. Thank you.
All right, thanks, Andrea. I think they had a bet with you to see if you'd stay under 10 minutes. And you failed, you lost. Yeah, you were close, but you still lost. So let me pull this up here real quick. Oops, wrong one. Here we go. So next up, a couple people that I've run across with just through my work as a cropping systems educator. And so I asked them to come share a little bit about what they're doing. So they're doing a lot of cool things. So they're going to jointly do this together. We've got Mike McDonald. He's a producer, Northwest Otoe County, southwest of here. He spent a number of years teaching and then is focused on farming now. And so he really comes from a background of learning. And I think that leads a lot to what he'll share with you here today. And so he's been heavily involved with a number of groups within soil health and no-till across Nebraska and across the state. And so I've worked with him in that capacity. And then we also have Zach Rigg. He's a soil scientist with Rigg Soil Solutions, is also a part of Vantage Ag Service and Avoca. So he spent the last couple decades, evaluating soil landscapes and really hoping to help growers maximize the agricultural productivity and restore the function of the native communities. So he spent time with the U.S. Air Force, the U.S. Forest Service, and is one of the founding members of the Nebraska Soil Health Team, so I didn't know that. But they'll talk a little bit about what they're doing with weather instruments, measuring weather on their farm, and what they're doing with it and why they're doing it. So I'm going to go ahead and turn it over. I don't know which one's going first. Looks like you are. So I'll go ahead and go to you, and I don't know if you like to stand close, but you can use this if you want.
Yeah, I'd better use this. I wander.
It's on, so just clip it on, and it should be good to go.
Yeah, I do a lot of wandering, so I better have something mobile. Which one do we use to move it?
The one on the right goes forward.
All right. Zach Rigg. I do some crop consulting, fertility consulting, and I do that primarily with Vantage Ag out of Otoe County. And then Mike McDonald is one of the growers that we work with. The catalyst project for us getting into weather, we wanted to get into weather for quite some time, but the catalyst project is this Big and Barley Men project. We applied for a grant through SARE and are evaluating barley as a crop in Nebraska as a weather and climate resistant crop. So I'm going to give you a little bit of a rundown on where, who, and what we are doing. This is the area that we're in, primarily in Otoe County and the surrounding counties is where we work. We service anywhere from 125 to 175 growers. And currently we have 5 weather stations. These weather stations are in Johnson and Otoe County. 4 of the weather stations are not necessarily in our most ideal locations for collecting weather data because they're tied to these barley projects for right now. So we do plan to relocate them at the conclusion of that study. So we're using an instrument made by Diacon. Diacon's a company out of Utah. They are an exceptional company that we're really happy with. They use a Modbus protocol for a majority of their sensors, which makes that extremely efficient. We get tons and tons of data out of them. It's quick, it's battery efficient. We've got some analog sensors on there too. A lot of these sensors are the same sensors that you saw on the weather stations throughout the day. We're collecting rain data as well. All of them have an embedded cell phone. We're actually going to start replacing those with some Wi-Fi modules to get rid of the cell phone on them. And they are solar powered, so we don't have to run power to them. The data that we're collecting right now, we have the data set at 2-minute intervals. So we're collecting a ton of data. That's transmitted back to us every 5 minutes through cell phone. It's put on a cloud server and displayed on a web page, a web service that the company provides for us out of Utah, which is Diacon Live. So all of our sensor data is displayed, and we have that set at 5 to 10 minute intervals depending on where the station is. The data that we're monitoring right now is soil temperature data, soil moisture data. We're getting the soil temperature data right now to calculate soil growing degree days, freeze-thaw cycles, depth of cooling, depth of warming. The graphic up here right now, this is just one of the pieces of information that we were trying to share. We were looking at different dates, and I was displaying here for some growers the temperature range. When did we have freezing? When did we have a thawing cycle throughout the soil profile? And this actually happens to show a period where we were 20 degrees cooler when the soil temperature was higher, because we had 6 to 12 inches of snow cover, than what we were whenever the soil was cooler. We actually had air temperatures that were 20 degrees warmer at the time, where we had colder soil temperatures. So just information like that we're trying to share with growers on what different environmental factors are affecting the soil for them. The soil moisture probes that we have are about a 2-foot long probe. They're a subsurface probe, so we're measuring about every 4 to 6 inches. We're getting a soil moisture, soil temperature measurement. So that helps us kind of build these profile graphics on soil moisture, soil temperature to talk to growers about. One too many there. Precipitation data, for that, we're collecting total quantity. We're also getting intensity data, so how hard did that rain event come? And with that intensity data, we're trying to marry that up with those soil profile, soil moisture logs, so we can look at before a storm, where we were at with soil moisture throughout a profile, after the storm, where were we at, and then compare that between sites. So our master plan is to get these relocated on farms that have different treatments. So one guy that's dead set on continuing to do tillage, another guy that is doing no-till, long-term no-till, another very progressive farmer that's doing some high-intensity management with cover crops, natural fertility amendments, really increasing soil biology, and then compare those sites across. So if we have a rain event that's very similar on similar soil types, then we can bring that back to a group of producers and promote different tillage systems, different residue management systems. Also collecting the temperature data, calculating growing degree days off of that, looking at first frost, last frost events, and then right now the primary tool that we're using from these weather instruments is the wind. Vantage Ag is a chemical applicator. Again, we're collecting data and seeing data in 2-minute intervals. So from a logistics standpoint, when you're loading a Terrigator and a tender truck full of chemical that you're going to truck 25 miles away, having a weather station right there in the neighborhood that's telling you, hey, are we picking up winds? It looks and feels like we're picking up winds. Is it really down there? Are they getting gusty? How fast are the winds climbing? We can look at all of the NOAA weather data, but also look at our own independent weather data and see what's going to happen, so we don't send trucks in the wrong direction. So from a private sector standpoint, what's the purpose of our investment? This was important to us because we've all been to the soil health conferences. We've all had extension educators talk to growers. A lot of growers will nod their head. NRCS office comes out, they're promoting soil health practices. A lot of growers will say, yeah, that sounds good, that looks good, I might try it once, but it won't work here. But for whatever reason, I'm not going to do it. But it works in North Dakota. But Iowa has sugar clay and we don't have that type of soil. So for us, we wanted it right in-house. We wanted it on farms that people know, with faces of growers that people know. So the excuses of the yeah buts go away. For us, it's another decision tool that we can start talking to growers about when to plant, what to plant. We continue to have growers that are looking at planting hybrids and varieties with longer growth windows. So we want to talk to them about the risks that are involved with that. We heard earlier today about the earlier growing periods. where maybe soil temperature, maybe air temperature is up higher earlier, is that the best indicator, independent indicator for our growers to plant early when the frost date is still staying the same? So it's information like that that we want to empower our growers to talk to them about risks. And then I kind of lump residue management into all of your no-till, cover crops, crop rotations. Residue management to me is helping growers make decisions on what's covering the top of the soil and how it's getting back in. And so we want to talk to growers about good practices that are going to benefit them in the long term. And then having live and local data to respond to questions. Growers walk in the door, they want to know, hey, can I plant yet? Is the soil warm enough yet? So rather than looking at a weather station from UNL at Meade, or looking at one at the Rogers Farm, or looking at one at Nebraska City, again, we have data right there on farms and faces that they know. So right now, we're getting way more data than what we can do anything with. Every 2 minutes, that's a lot of data to collect. We have some plans to develop some products. Actually, April 1st, we're supposed to have a release on the Diacon Live site on some of the requests that we've had for some agronomic upgrades for certain reports and measurements that will be useful to growers, useful for us to kick right back out to growers. And really, we're just trying to pay attention now so we're ready for when things do change. I know there are models out there. I don't know enough about them to know which ones to trust. I don't know how high to trust, how low to trust, but we're just trying to be aware and pay attention right now so we're ready for whenever things do happen. And our biggest challenges, we talked about pests earlier, that is a challenge for us. These are tools that we're trying, again, to come up with some calculations, looking at recent research and other information to help make decisions and help make growers aware of additional pest risks and to get ahead of pest treatments. As new pests are introduced into our agricultural ecosystems, and there are restrictions on pest application, we want to at least make them aware of biological controls, cultural controls, rotational controls, and with that have realistic data, realistic goals on what our control thresholds are and what's economically viable to control with. As I mentioned, what got us started on this on the weather stations was this barley project, and that is, we often hear about, let's diversify the rotation. Stop just planting corn and beans. Why don't you throw wheat back into the rotation? Why don't you introduce a new crop? Well, we tried, and we are trying. But I'll be honest with you, one thing that I underestimated with this project significantly is the marketing challenges. Bringing a new crop into an area that doesn't have it, developing a new market, you saturate it very quickly. It's a real challenge. The reason that there are people that make millions of dollars marketing is because it's really hard. And this is something that we've found out. Another challenge that we have is competitive ag marketers. So you have the co-op, you have other ag advisors, you have equipment salesmen, all of these people out here giving advice, and a lot of it's really good advice. They're trying to help. What we run into is a lot of the advisors are giving advice for the problem today, the problem right now, and they have really good solutions for that. One, just as an example, deep tillage. Everybody wants to run a ripper. They're fun. They're big. They are fun to run. Everybody wants to put a ripper in there and rip the field because you get a yield bump the next year. There's data that supports that. I'm not going to argue with that. But with our weather station data, we also have data to support you're doing it at an optimum time to compact, to cause sidewall compaction and deeper compaction in the soil profile. We also have weather data now to support how deep is our freeze-thaw cycle to relieve some of that compaction. So if we have different residue systems, if we have shallower freezing depths every year, if you're your compaction, your tillage compaction deeper in the profile, we want to advise guys and let them know what the risks are, the long-term risks, not just the immediate impact of doing that action. Again, we have different growing seasons. Crops were in the ground, in some cases still in the fields until December, January this year. If your plan is to go in and do an action like deep tillage, it's going to be difficult to do that if you're still harvesting in January. So it's just information like that that we're trying to pass on, and this is giving us the framework to do that. I'm going to pass it on to Mike. He's the one actually that puts his money where my mouth is. So I'll just pass it on to him.
Thanks. I'll give you an extra 5 minutes. How about that?
Whatever you want.
Because you've only got 3 minutes. I'll give you. I'll give you more than that.
You're a good guy. Does this work? Okay. Well, thank you, Tyler. It's been a really good day, and I really appreciate the opportunity here. I'm no expert. A lot of you here, I know some. A lot of you, this is brand new, and there's all kinds of good things going on across the country in Nebraska. So this is just one perspective as we look at things, to take a look at it there. This was taken, we think about the growing season. So I had several good friends say, look at it 4 seasons. So underneath that, we've got growing going on. And that's what we all want. Rather than just the growing crop season, you want something throughout the whole 12 months. Okay, Zach talked about this a little bit. And what we really want to talk about in this part is Andrea. We talked about what she was doing. We wanted to complement the rationale with the actual practice. And again, we're not trying to do anything unique. We're just trying to build upon best practice. So if you look at the temperature there, I purposely took the day when we had the bomb cyclone. When you saw that barometric pressure going to 28, you knew something was going to happen historic. So if you look at that, the date there, the arrow, you can see my temperature of my soil, and you look up above, that's actually what the rain velocity was doing. Look at the temperature of the soil as that went through. And that was just, not too many days ago. But put that in mind as we go, what's happening in the soil below the ground. That's the top priority there. You see the temperature? We still got activity going on. And that was going on most of the year. Okay, Zach brought his son. Derek, can you raise your hand? Okay, I think that's pretty cool. He's involved in his son. He could be home spring break from Millard, but he's here. And I think that's pretty cool. He's working there. Okay, the 5 main objectives. Not just looking at corn, soybeans. I'm not against corn, soybeans. I'm a lifelong Nebraskan. Where you saw the slide from Andrea, I grew up 45 minutes west of there. And so my cousin yesterday by Loop City, Dannebrog, probably saw those pictures. If you get a chance to read an article in the Kearney paper, Richard Panowitz, he's a neighbor. My cousin has a backhoe. Yesterday he buried 40 cattle. You know how most of them died? Ice chunks broke their legs. Can you imagine? Going down is right by the loop. It's terrible. So I grew up right by there, and there's just unfold things going to be coming down the pipe. Okay, livestock. I had a good friend. I want them to pee and poop. I wish I could collect the methane gas Galen was talking about. We want to look at value-added steps. We don't want to just be tied to the futures market. Worried about what's going on with tariff in China. We want to control what's going on with marketing, because marketing is everything. The bills are tight, very tight. We want to learn together, and we always want to build roots. So think of roots versus shoots. We don't want to worry so much above ground. It's what's going on right now today. We want sugars. Okay, this is a famous picture. This is at DC at the National Botanical Garden. If you ever get a chance to see it, this is a cool one. Actually, that's at Smithsonian. I'm wrong, sorry, if it's still there. It's a really cool picture. We want those deep roots where we used to be in Nebraska. We've gone from 6 foot of organic matter level to less than a foot in a lot of cases. Okay, I don't want to take credit for this slide here. a couple weeks ago, I heard Dan Forgy from South Dakota. They have a really neat group called the South Dakota Soil Health Coalition. I know several people involved in that. We're looking at the top part there. If you look at rye, wheat straw, we are focused on carbon. But more than just carbon, I went to Kansas 5 years ago. They were doing barley, and when you walked across barley fields, barley has one single stem, and it was like straws of water. We walked across it, and this was July. He had just planted soybeans. That water flicked out at us. And so as we've been researching, we purposely are choosing our crop rotations tied to different types of lignin. And that's really what we're trying to concentrate on. So if you look at barley and wheat and straw, that's what we're trying to focus on. The higher, the better. This is another station. I've got 4 different farm sites. So this is another one to compare to our weather station. And Tyler helped me. There's a weather project. Alabama?
Results here, actually.
Is he really? Okay. Where's he at?
Part of the, I think in the Arkansas group.
Okay, so there's a group of weather stations. They're setting a project from Arkansas up to Nebraska. So Tyler helped me, and we've been putting that up. We're trying to get strategic across southeast Nebraska weather stations. And one thing I wanted to emphasize, we are all dryland. I'm on the Nemaha NRD board. It's a real privilege. But as I talk to people about irrigation, I grew up in central Nebraska. We had irrigation on our farm. I moved to Imperial. I worked for the first guy, Dennis Kuhneman, had the first lateral pivot in the state. He does all popcorn, ships across the world now. We have pretty much dry land. So we're focused on what we can do in dry land, not necessarily irrigation. Residue. Rich Russell from Arrow is just a very knowledgeable guy up in dry country and Broken Bow. But again, we're looking at residue. Look at oats, look at rye. Corn has a lot. We want to get as far from soybeans in a row chase possible. Not that it's bad, but if you go drive by the fields now, you see what's going on in soybean fields. Corn was a little bit luckier with all the rain we had, but we want something growing. So rye's been growing now for a couple weeks now. It's starting to kick up, and our barley is too. If you don't know Jill Clapperton, she's from Montana. She is a world-renowned researcher on different types of rotations and sugars. So the more we research, we're trying to get to those different exudates. Carbon, sugars, sun. And when we choose our rotations, we're trying to go backwards of what we're doing. But if you look at barley and oats, they're outstanding for mycorrhizae. And that's what we're trying to do as much as possible. Tyler, can you tell when I got 2 minutes? Okay. My wife took this yesterday, and so basically what this is, this time of year the soil is mostly frozen. So this is just a probe. You can go out in your soil. If you don't have one of these, I'd encourage you. So that way you can tell how your soil infiltration is and your compaction level. So basically yesterday on the left there, we took this yesterday, and that's barley just starting to pop up, and we interseeded clovers. This is our 5th year of having something growing year round. So there on the left before, there on the right, I was able to push it down 3 foot in supposedly frozen soil. And this is very average soil. Now, this is eroded Pawnee Wymore, but I could have gone all the way in. And before 5 years ago, we were lucky to be able to poke the ground. Okay, manure. I'm not going to get through all the slides, so some of these Tyler was going to put up. You can look at them. Prairieland Dairy, we use their manure and compost. So we're always looking at value-added times when we can put manure on instead of going to co-op. Wheat, barley has a 10 to 15% yield benefit the next year in your corn. So we're trying to look at things, not just wheat, because wheat's $4.52 I think today. You can't pay your bills, but we're looking at that. This was delivered. We're going to put in different ways we can do it. You can't do this on a large scale, but we're going to do another 80 acres this year. So then that way we're trying to look at how we're building carbon at different times of crop rotations. This is one of our partners. Randy couldn't be here. That's a fun picture of his daughter. That's a finished product of barley. So barley's one of them. Barley's different. Ray Ward's really helped us. Barley's low protein. This is malted barley. We've talked to several breweries, and we've got one. We hope that we'll have a field day with them. We used their beer last fall, and if we don't, then we'll feed it or cover crops. That's his daughter. She's doing that in a Forage project. Okay, second area is soybeans. A lot of you seen this. This is when we plant it with our rye residue. This is what it looked at when we harvested. Now that was a perfect year to fly it on. It was almost too tall at the combine. but that was an all right problem. Okay, this is Tyler, and on the left, Tyler's given directions to Jenny Reese to install the sensors. She's working hard there, Tyler. She's not here, I got to tease her. Okay, this is corn, the third we normally do, barley, soybeans, corn. Okay, again, residue. Tyler's been a big help, and my local NRCS, Mike Bergert. We installed water sensor moistures. We're in our third year in dryland. We want to look at the different areas of weak soil, the better soil, and particular types of cover crops. Here's what it looked like when we harvested it. If you know your cover crops, there's radish right by the corn, there's clover right to the right of that, and then that's rye. And that was a perfect year to fly it on. Okay, the fourth, Galen talked about biochar, where Galen is. Okay, we got a grant last year from the Nebraska Biochar there. And so this is actually a garden across the way in the middle picture. That is where we grazed it. And actually, if you see here, I ordered the same biochar that Galen did. And so we did it in cropland, our garden, and pollinators. And so that's pollinators, and that's a tote. It's not feasible doing a large scale, but we wanted to look at the carbon because it's one of the highest forms. In closing, don't go by these organic matters. So those of you that know organic matter, you're going to look and say, I just made these up. Okay? So if you look at the organic matter, the basic soil, biochar, and compost, that's unrealistic. That was in a controlled area. But if you look where we started, 3.4, and you look at my non-treatment, 5.6, I'm very, very pleased, and most people would be. And I'm no better than anybody else. It's just being intense over 7 years now. But what I most like is down the bottom. You look at my fertilizer recommendations, that's where we're headed. Ray Ward looked at it. Lance Gunnarson's working on his PhD on soil health at Ward Labs. I think that's where we want to go today. I want to cut back those nutrients to get to different diversities, and that blew me away. So, the fertilizer recommendations, I like seeing a lot of zeros there. We got a site up there. Gary Lessing's not here today, but Gary's a big part, and so I really appreciate the opportunity, and Tyler's been a key part. And I appreciate the opportunity. I go very far.
Okay, thanks, Mike and Zach and Andrea and Galen. We're out of time, so we might just save the questions for breaks if you guys are cool with that.